Anybody going someplace fun next week? Anybody going anywhere next week? Everyone's staying here? Anybody else? Everyone's staying here. Really? Okay, so we're where we left off talking about control flow. So control flow is how a programmer decides what instruction should execute next. And if you don't say anything in a program, it's sequential, but you can use things like for loops and if statements, which are the two things we're talking about specifically, to change that control flow. We talked about last time how every instruction set has to have at least an instruction that will jump to a different place in the program conditionally based upon some dynamic value that the program calculates. Every instruction says it has to have that. If it doesn't have that, it's not Turing complete. There'll be programs that are computable that can't run on it. We introduced two of those. So there's branch if a register value is equal to 0. And there's another one, branch if a register value is greater than 0. And then we also had two unconditional jumps, branch. And we talked about the difference between jump and branch. So branch is a 2-byte instruction that uses PC relative addressing so that you can jump to nearby locations with a small instruction. Jump uses absolute addressing. It's a big instruction, and that's what we'll use for things like procedure calls. So, any questions about that? And then we started looking at for loops, and we'll finish this and look at if statements in a second. Working from C to get to assembly language using a template. And I'll go over that in a second. But what's just as important, and actually quite a bit harder, is to be able to go in the reverse direction. So we're going to spend some time on that today. It's the kind of question that you might find on the midterm. So you probably reach it. Okay, so this is the for loop we were looking at last time. The simple loop goes through an array, 10 things, adds up every element in the array. Every for loop can be converted into code, C code, that doesn't have the for loop, just has go-tos following the template. So the template has different parts. So the first part, the part that comes before the loop starts, is initialization of variables. And so this happens when, this is the part of the for loop that comes before the first semicolon. Okay? So in this case, it's I equals 0. And then you have a label. And in this case, because we're going from C to assembly, I know that this loop's I call the label loop. When we're looking at later assembly code, the reverse direction, guys, you won't necessarily have the word loop there, so you'll have to have some other way to know that that's a loop. And then the first thing at the label is a test to see whether you should do the loop, and if not, a jump out of the loop. And in this case, we're using the label end loop to indicate the next instruction after the loop. And then there's the body of whatever the for loop is, and at the end, there's another part which is typically incrementing a variable. So it's changing the value of a variable that you're using in the continue condition at the top, and then jumping unconditionally back to the top. Okay. So when later we look at assembly language, what we're going to be doing is looking to find that template in the assembly language. So the assembly language is going to be produced from this. Before we got to assembly, we transformed this in two ways. So first, that comparison at the beginning of the loop has to be normalized so it's a comparison to 0, because that's the only comparisons we have. So in this case, I'm comparing to 10, so I'll have to, in the normalized case, subtract 10. So I've got this I that I'm comparing to 10, well, I'm going to put I in t and subtract 10 from it so that I can jump when t is 0. And then the other thing I did was modify the code so that it might be possible for the body of the loop to avoid access to memory by keeping values in registers. So I'm using a variable name with a prime to indicate that that is the value of the variable, but it might just be in a register. And so the basic pattern to this is that before you do the loop, you'll copy from the variable in memory, that's the expensive thing, into a register, which here I'm using prime, so I do that for these 3 things, plus also t doesn't have to be in memory, so that also might be a register. And then I only use the primes inside the loop. And at the end, for things that were variables, I have to update them back to memory. I copied from the register back into memory. So at the top I have, s prime equals s. At the bottom I have s equals s prime. And in the middle I might be changing it to prime. Does this make sense? Now, you may or may not actually put those in registers. It's going to depend on how many primes, different primes you have. In this case, I have fewer than 8, so I have enough room in every register for them. Question?
And that was my question. What if the loop
Yeah, so let me just finish that sentence and then I'll have your question. So, and so what I did here is I just went down this list, and the table in the upper right indicates the assignment of variable to register. And then I can take the C code and replace it with assembly code. Mostly there's a one-to-one correspondence. When accessing variables, it takes 2 steps, and there's some other things there. Obviously, the assembly code is a lot harder to read because lots of reasons. But in terms of the primes and register names, you'll see that in the assembly code, like for example, I have this S R2. From the table, you see R2 is S prime. And so that is that. Yeah, but you had a question. The question is?
Yeah, my question was, what if the loop needs more registers?
So what if you need, like I write down all the primes and I've got 20 primes. I only have 8 registers. In fact, you'll see that you don't usually have all 8 registers even. So then you would have to decide which ones will be in registers. So the goal here is to minimize memory access inside the loop body. Why is that an important goal? Why is it important? Yeah, so memory access is slow, so if I minimize the memory accesses in a piece of code, it makes the code run faster. Why is it important to do that for the body of the loop? Because it runs multiple times. Yeah, so this is an optimization. I'm looking at a piece of code. Say, this code is more important to speed up than other pieces of code. So if I have registers that I'm using like outside of the loop, I would reuse them now for the loop body. If the loop body though itself requires more than 8 registers, then I will have to go to memory for those, like the 9th register.
Does it cost like that much to have an extra register? Like, why wouldn't you just implement more registers?
Yeah, so this is a really good question. Does it cost that much more? This is a total aside. This is how I get out of sync with the other section. So let me see if I can say this very quickly. It's a really good question. So obviously you want more registers. x86 only has, so the instruction set that runs on your PCs only has 8. But you remember that it's a micro engine inside, well, I don't know if you remember, but it's actually implemented as a RISC processor that has many more than 8 instructions. So there was a period of time where like the ISA only had 8, but it was really running with more, and there was a translation that was happening, which isn't so great. But the reason it was stuck with 8 was that compilers were compiling to that ISA. At some point, Intel devised a modified ISA, which is called IA 32/64. And they added 8 more registers, and they changed a bunch of other things. So yeah, you want more than 8. We only have 8, because we only have, I don't know. We have 4 bits. Yeah, good one. And 8 turns out to be really, 16 turns out to be a really good number. Few instruction sets have more than 16, unless they do that for a special reason. Great question. Back to the main topic here, which is, now we get to this assembly code. This is where we left off last time, and I asked the question as we were packing up to leave, is this easy to read? And the answer is no. And so we're going to talk about that briefly now, and then we'll come back to it after we do loops. And the reason that this is hard to read, first of all, in the assignment, in the midterm, you won't get the comments, and this will just be L0 and L1. The comments help you to read the code, so obviously you want to write comments. And you want the comments to be as high level as possible, which means that they relate back to C. What you're really trying to do is understand assembly language as if it was C. And so if you get good C-like comments, which many of these are, for example, when you're accessing an array, you just name the array and you name the variable. You'll have to invent variable names often in order to do that. But that's fun, because this will help you read code. I'll point out one thing here that we've done, is go to +8 or go to -14. That, you would never write a comment like that. That's just to emphasize what we talked about last time about PC relative addressing. You would just say, instead of go to +8, you say go to n and -14, go to But even if you get all the comments right, it's still too hard to read. And the reason it's too hard to read is that the structure that exists there is not explicit. And there is structure there, right? So if we look at the jumps, we can see that, well, there's one jump that jumps in the forward direction, and one jump branch that jumps in the reverse direction. As soon as you see that, you know that this is a for loop. There's nothing else that uses branch to go in reverse. And once you know it's a for loop, you know that that for loop has different parts. It has the initialization part, and it has the test to see if you should exit part, which ends with this jump. And it has the step part, which is usually an increment or a decrement, and a branch back to the beginning. Okay? Just drawing those arrows and drawing those boxes now makes it easier to read this code. And the reason why has to do with structure and the fact that now every chunk of code that I have to look at is relatively small. And this comes to the reason that structure is important is that it allows us, when we're trying to understand something, to focus on a small set of things at a time. And if you just have all of the instructions, without the structure, you might be forced to try to essentially understand all of them at once. And the human brain can't do that. Human brains, young brains like yours, can only attend to roughly 7 things at the same time. So you might, if you're very smart, and you have a very young brain, and you're not distracted by anything else in your environment, you might be able to understand, or have in your mind, the meaning of 7 instructions at once. But probably you are distracted, and your minds won't be young forever. You're like me, it's fewer things. And so the purpose of structure is so that I know where to focus. Every one of those boxes only has a few things in it. The total number of boxes is relatively small. It's the same thing when you're writing prose. Right? A paper that an essay is divided up into paragraphs, paragraphs into sentences, paragraphs are grouped together into sections, sections into chapters. Why do we do that? Same exact reason. So you can focus your attention on small sets of things at a very low level, at a medium level, at a high level, so. Right? So this turns out to be really important. Yeah, so now it will depend on, so this is an outstanding question. So what about this thing here? I equals I prime, does that matter? And it depends. If that's just like a local variable and it's gonna go away, and no other later piece of code could ever read the value of that variable, then it doesn't matter, you don't need it. You can just have it in a register and just forget about I. What is it? But if it's a, yeah, so, but if it's a global variable, which in this case I think it was, it's not declared here. Notice I don't know if I never showed the declaration, but if it, in this case it was a global variable, if some later code might try to read that variable, then you have to update it. And local variables normally we don't worry about. Keep them registered. Any other questions? So we're going to come back to this idea of structure in just a second. We're going to do the other control flow mechanism we're going to look at in detail, which is the if statement. So, you know, if is, the general form of if is, you say if, some condition, and then you have some then statements. And some else statements. And we know that only one of these will execute, and which one executes depends upon the value of the condition. In this example, I'm going to look at A, computing the max. So if A is greater than B, the max is A, also the max is B. So there's a template for if statements as well, except for loops, and the template is, well, first compute the condition. I actually have to compute the complement of the condition in this example, because what I'm going to do is compare to 0 in order to jump to the then case. So I've decided, and we'll talk briefly about why, it's mostly arbitrary, but it's the standard thing to do, to put the else code first. So I say, well, if the condition is false, if the complement of the condition is false, in other words, the condition is true, then jump to then. Otherwise, don't jump, do the else, and then at the end go to the end. Skip over the Now, if I only have then that else part isn't there, and I just skip over the then case if I don't. And so there's sort of two forms of that. We'll see the other. So there is a reason, there's possibly a benefit to this order, else, then, as opposed to then, else. Either one I could do. But there may be a benefit to this one if it turns out that if you profiled the execution of all the programs in the world and looked at if statements and the probability that the then part executes versus the else part executes, and we find that then parts tend to execute a little bit more frequently. Which turns out maybe it's true, kind of true. Doesn't matter, I just want you to answer the question, why, if that's true, is this better? If the then part executes more frequently than the else, why is this structure better than flipping it around and doing the else part first? Let's talk to each other. Anybody see what's going on here? Why else is a little bit more efficient than then is more efficient than else? Who thinks they see it?
Is it because else has to compute two lines instead of just one then?
Yeah, exactly. So it's just simply, if you count the number of instructions that execute, in both cases, you'll get different numbers. So in the then case, I would execute this instruction, 1, and then this one, 2, and then this one, 3. 1, 2, 3. But in the else case, I have to do one extra one. I do this one, I do this one, I do this one, that's 3. Plus I have to do this one to skip over the then case. So in the else case, I skip over, the then case, I skip over the else case. And then when I'm all done, I'm ready to go. I'm already at the end. But in the else case, I don't go, skip over the else case. So this jump actually doesn't happen, but I still have to execute the instruction, and then do the else, and then do the skip. So there's this one extra instruction. It's not that big a deal, but it's an instruction. And I only had to do this so you could take a minute and reflect on what's going on. Okay, so let's now do what we did before. We'll start with this. I'll first convert it using the template into C code that doesn't have an if in it. It sort of has if, but it's not structured the same way it's using go-tos. So I say go to then if A is greater than B. In the then case, I say max equals A. In the else case, I say max equals B and go to A. That's the template. Now I have to normalize that. So the first one thing I have to do is normalize this A greater than B condition to a comparison to 0. So one way to do that is what I've done here is I'll introduce a variable C prime, so it'll just be a register, and I have C prime be the difference, A prime minus B prime. And then I'll jump when C prime is greater than 0. So when C prime is greater than 0, what's the relationship between A and B? A is greater than B, right? So that's go to if A is greater than B, which is what I wanted, but now it's a comparison to 0. And then the other thing I did was the prime stuff again. So in the beginning, I copy A into A prime, B into B prime. I use C prime for this, because that'll just be a register. And at the end, I copy max, which is the only thing that changes here back, max prime back to max. And this is the assembly code. And so I say, I'll put A prime in R0, B prime in R1, R2 will be the difference, R3 is going to be the max. And then we could comment this code, so I'll just write the comments here, let's read it. So the first line puts the address of the variable A into register 0. The second line, register 0 now is the value of A prime. Same thing with register 1, it's B prime. And now I'm doing this calculation right here. So I'm going to copy B into register 2, and then I'm going to complement and increment B, which negates it. So now at this point, C prime is minus B, which I can see from the comments. And then I'm going to add A to C prime, A prime to C prime. So now C prime is A minus B. And then I say branch on greater R2 to then. So this is branch to then if R2 is greater than 0. So go to then if A is greater than B. So you see the high level comment over here. This is a lot easier to read than that one. And then the else case, I say max prime equals B. So move B into R3 and skip over the then case move A into max. And then the last step is get the address of the variable max into R0 and store max prime into max. Okay. Questions about that? Super easy to read, right? Okay, so now I have a little exercise to solve them together. This is like something you'll see on the midterm. Piece of code, there's no comments, the labels are nonsensical. The only thing you won't get is variable names. I haven't actually given the variable names here. You won't even get that. And you'll be asked the question, what does this code do? So perhaps the first thing you would do would be to put comments in. So I'll put the comments in. And then you might go through a couple of iterations on the comment. So, there's a point here where I'm accessing a sub r0. I might give that a variable name. So I've invented some variable names here and replaced the registers in the comments now. They're all C variables. Now I invented those variable names. They didn't show up anywhere in the assembly code. But it makes the code easier to read. The next step, so now I'm going to switch over to the document. Want to switch over. That's not on. The next step is to look for structure. So that's what I want you to do. Hopefully, some of you brought the slides, and maybe some of you have a device you can draw on. So get together in groups of a couple of people and work through this. It helps to be able to draw arrows and boxes. Oh, I don't know. You can probably read it. So, draw the arrows. Draw the arrows and draw the boxes. Are you taking a picture? Yeah. I was just printing these out. You want to take a picture? Yeah, just Okay, so let's do this together. So the first thing to do is to draw arrows representing all the branches. So just go down, here's the first branch from here to L9. Keep going, here's the next branch from here to L1. And here's the last branch, a branch from here, back up. So, there are two different templates here that emerge together. One is an if statement, one's a for loop. These two lines, this one, the reverse branch, that's always going to indicate a loop. And this one, which is the branch out of the loop, so this is, those are for the for loop. And I might now actually change this label, because I know